here we go. Right. So we are going to do this problem set now. Okay, now this problem set has a lot of layers. Layers means there's other things that I have to explain. Now, I hope you did download this question from Avenue to Learn. Okay, so let's zoom in. So this is example number 1. So I took this from PO. So this is a PO question. Okay, so what you see is you see a structure over here, a beam held vertically ABC, and then you have a cable at point C. You have a cable at point B, preventing the member AC for rolling down this direction. At point C, you have 25 kilonewton. And then from A to B, what you see over here is what we call a gradient distributed load. Okay, what you see is a gradient distributed load with maximum magnitude of 20 kilonewton per meter. Okay, so this is what is 20 kilonewton. Now, when you guys were taking, when all of you were taking 3SD3, did the instructor teach gradient distributed load? Yes or no? Anyone, please?
No.
No?
No.
Okay. Yeah, thank you
Oh,
for, yeah. Okay. I will not leave you out to dry. I'm glad that you're telling me no now. Okay. So I'm going to explain what is gradient distributed, but there are more things to that. Okay. So the first thing to see is rigid. Okay. So first of all, the words like this mean something. Okay. In structure analysis. Okay. What do we mean by rigid? Vertical bar ABC is supported by a 20 millimeter diameter pin at point A and two 12 millimeter cable at point B and C. Okay, so we know that we are, so you have to write down whatever information that you have. So we know that we have at point A, we have a pin. Okay, at point A, we have a pin and it is 0.02 meters. And then we have cables at point B and C. As you can see over here, point B and C, we have cables. So diameter of cables, okay, diameter of cable at point B and at point C. So we know that the cable is 12 millimeters, so it's 0.012 meters. Convert them directly. Then other things that we are given is like the length of the cable at point B is equal to 4 meters. The length of the cable at point C is 2 meters. Okay, and then what is given is also telling us that we are also given that the yield strength is equal to 400 times 10 to the power 6 Pascal. And then we have a Young's modulus of 200 times 10 to the power 9 Pascal. Okay. So the question is asking us, okay, right? And then the concentrated load of 25 kilonewton, and then you have a distributed load of 20, as you can see down here. So the question asks us to find the forces on each cable. Okay. And then we are going to also find, right, the corresponding horizontal displacement at the top of the bar at point C. Sorry, at point C. I will not do question C. Okay, I'm not attempt question C. It's really easy to do, but I'm not going to attend this class because I have not taught you shearing stress or shearing force yet, so I'm going to skip that part. So this is a typical problem that you'll see in a PO exam. So this example is a PO exam. Okay, and it's already, this is the first week, and we're already looking at a PO exam already. Okay, so because the content taught, I think all of you can handle. Now, the first thing that we're going to do is what it states that it's going to assume right member ABC is rigid. Okay, it's making the assumption that it's rigid. Okay, and we obey we obey. But when you make that assumption, what does it mean? Okay, so if this is our member now, if I were to draw a member, right? So this is our member. So this is our point A. And then somewhere up here, this is our point B. And this is our point C. And when we assume that it's rigid, what are we trying to do down here? The deformation is going to be a straight line. Okay. So i.e. over here, right, what you see over here, this is your B prime, and this is your C prime. So by assuming that the deformation is a straight line. So this is why we use the word rigid. Okay, something that's rigid. Okay, when something is rigid, it cannot bend. Okay, my wife say I'm always too rigid. Yeah, I cannot bend. Okay, and that's my problem, right? So in real life, okay, it's not going to be rigid, is it? Right? In real life, you're going to have some deformation. So in real life, I'm going to sketch out. Okay, this is just a sketch. You're going to deform this way. Okay, you're going to deform this way. Is the color the same? Gee. Yeah, I forgot to tell you guys I'm partial color blind. Okay, so that's why I always fail my chemistry. The practical will say what color is the solution. I usually taste it. Can't tell by color. So anyway, so this is the actual deformation. Okay. So for now, as we are in today, we're just going to assume rigid. In probably on the 8th or 9th week, you are able to calculate the actual deformation. So let's start from something simple first. Okay, so you all see the difference, right? So as rigid, we assume that the deformation is a what? It's a straight line. Okay. So the next thing that we're going to do, so you understand the term rigid now. Okay, you understand the word rigid. Now, any questions so far?
Nope.
No.
No. Okay, good. I want to drive the point that you know. So the next thing that we're going to do is we're going to draw a free body diagram. Okay, we're going to draw a free body. We're going to draw and we're going to draw. So this is the first time you guys have seen this. We're going to draw a multi-body free body diagram. Okay, we're going to draw a multi-body free body diagram. So if we were to, so we have, I'm going to draw our member. So our member, so I'm going to go into a different mode now. Okay, so we have a length of 3 and then 6 meters. Okay, so this is our member. So over here, this is my point A. Over here, this is our point B. And over here, that is our point C. Then as usual, we have to draw our transformation. We have to tell the marker or your client, you're assuming that this is X, this is Y, and then this is rotation about Z. Okay, there's your assumption. So that is your one of your body, and we know that over here we have a load at point C in this direction, and we know that this is 25 times 10 to the power 3 Newton. Okay, and then we have a distributed load between point B to point C. However, the distributed load, okay, will be somewhere here, and this over here is what we call our equivalent load. Okay, the equivalent load is not exactly acting at point B, okay, but it's acting somewhere in between point A to point B. Let me complete drawing the multi-body distributed load first, then we come back to the equivalent load. Okay, so the next one, we have a cable. So we have a cable doing at 2 meters. Okay, the cable is, yeah, the cable is 2 meters and 4 meters. So we have a cable. So this is our point C and our point E. Okay, so this is our point C, or cable C. And then at point B, we have our cable B. Okay, cable B. Okay, and we know that cable B and C will be under tension. Okay, we know that cable B and C will be under tension, and this is under what? Tension. Why that is the case, right? Because without the cable, right, the structure will go in this direction. Yes or no? Right? Without cable, it will fall. Right? Without a cable. So the cable is preventing from going towards the left. So that's why it's stretching. Okay, so this is very obvious that it's under tensile. Okay, so that's our cable. So we know that this is the direction of our cable. Okay, in fact, I should have put my cable slightly higher. So we know that this is in tension. Right? So we know that this is in tension. Right? And then cable B is also in tension. And when we apply Newton's third law, action equal reaction, same in magnitude, different direction. This is the direction of your FC. relative with reference to your member ABC. Okay, and this is your FA. Okay, so there's your FC and there's your FA. So this is how you draw. So sorry, I'm not done yet. Then we have another load over here, another reaction over here. We have our reaction AY, right? And then we have another reaction AX.
Shouldn't it be FB instead of FA?
Oh, you're right. Your name,
My name's AY.
last name,
Hashi.
H.
HASHI.
Hashi, 1 pint of beer. If you cannot drink, 1 pint of orange juice.
I'll have the orange juice.
Orange juice, okay? Okay, so if there's no coronavirus, we will go for the orange juice. If not, still come and see me, okay? Every mistake that I make, you get something to drink, okay? Oh, before I go on, someone asked on a question, what will happen if the isolation or the lockdown gets lifted up? If it gets lifted up, I will ask you again, do you prefer to have your exam face to face, or you want to do it online? Okay, I will ask from there. I'm flexible. What I'm saying is I'm flexible. I'm not saying that I'm locking into one, but we have to follow McMaster's policy. Okay, so that's the other thing. Right. So the equivalent load over here. Okay, next I want to focus the equivalent. So I think the most difficult aspect of this example is the equivalent load. Okay, is the equivalent. So the equivalent load over here, okay, is basically half times by 6. Okay, why 6 is because the distance, the length is 6 meters, and then multiply by 20 times 10 to the power 3. And why 20 times 10 to the power 3? I do apologize, I will space out. Half times by 6 times by 20 to the power 3. And the equivalent load will be equal to 60 times 10 to the power 3 Newton. And the distance from here to here, okay, from here to here, all of a sudden I cannot write on